Okay, so before we start today, does anybody have any questions? Okay, so this is our last real class where I'll be talking about new material. Next week there'll only be one class, and in that class I'll just go over one of the final exams, I think, as a sort of prep. So today we're going to do something, I won't say completely different, but something that we've been building up to all course. And we're going to talk about this thing that goes under the name the probabilistic method. And so the probabilistic method is a technique that was developed and used extensively from, let's say, the 1950s until now, that really revolutionized combinatorics, the way combinatorics was done. There's a famous figure associated with it, Paul Erdős. Anybody ever heard of this guy before? So he's a famous mathematician, one of the most prolific mathematicians ever. Famous for posing a lot of problems, and he's basically a guy who devoted his whole life to the study of mathematics. He didn't really have a home so much. He traveled around visiting researchers all over the world, working with them. And one of the things that he really worked with a lot was this probabilistic method. And there was sort of a joke in the 1960s or so that Paul Erdős would go to a conference, mathematics conference, and people would be giving a talk, someone would be giving a talk. Erdős would be falling asleep in the audience. That's something he was famous for, falling asleep all the time. And during the talk, the presenter would make some conjecture. For example, the presenter would say something like, "Oh, I believe, I conjecture that every n-vertex graph contains an independent set of size n or of size root n or a clique of size root n." And then Erdős would wake up and start scribbling on a paper. And then at the end of the talk, the presenter would say, "Okay, does anybody have any questions?" And Erdős would put up his hand. And the standard thing would be, nearly every graph is a counterexample to your conjecture. This was the famous thing. And we'll see that today. We'll see how this happens. So people think something must be true because they were unable to find a counterexample. And it turns out actually that sometimes counterexamples are not easy to find explicitly, but are actually easy to find using this probabilistic method. So there's nothing very deep about what happens in the probabilistic method. There's sort of two versions of it. So here's one of them. So consider some event A. So that means it's a subset of the sample space. That's what it means to be an event. So if I can prove to you that the probability that A occurs is bigger than 0, well, that means that the size of A is bigger than or equal to 1. Right? There's at least one thing in the sample space S that's in A, so the size of A is bigger than or equal to 1. Why is that? Why is there at least one thing in the sample space that's in A? Because otherwise, well, the probability of A would be equal to 0. Right? Because remember, probability of A is just the sum over all of the things that are in A of the probability of that thing. So if A is empty, meaning its size is 0, well, then the probability of A has to be 0. So if you can show that the probability of A is bigger than 0, that means there's something in A. So that's one version of it. Another common version of it is you take a random variable, x, from S onto the real numbers, and somehow you figure out the expected value of that random variable. Okay? And what do you conclude from that? You conclude something quite weak, which is that there must be something in S whose value, when you apply this x function to it, is bigger than or equal to the expected value. Okay? So all that's saying is in this set S, everything is this x assigns each thing in S a particular number. The expected value is the weighted average of those numbers. So there must be something in S which is bigger than or equal to the average. Okay? So it's like me being in this room, and if I try to tell you, oh, the average height of a person in this room is 7 feet tall, to disprove that, you don't have to go and figure out everyone's height, measure them all, add them all up, figure out what exactly the average is. You can just look and say, look, there's nobody in this room who is 7 feet tall or taller, therefore the average can't be 7 feet. So, on the other hand, if I declare, if it is true that the average height of people in this room is 7 feet tall, then there's at least one person in the room who is at least 7 feet tall. That's all that this is saying. Okay? And the interesting thing about this probabilistic method is you use probability, but you use it to prove things that have nothing to do with probability. So you use them to prove that certain things exist. Okay. So let's start with a very concrete example. Here's a theorem. Let G be a graph with M edges. Then the vertices of G can be partitioned into two sets, A and B, such that at least M over 2 edges have one endpoint in A and one endpoint in B. Okay, so here's an example graph. So the statement of the theorem says nothing about the number of vertices in the graph. In this case, there are 5 vertices in the graph. It talks about the number of edges, and the number of edges in this graph is 1, 2, 3, 4, 5, 6, 7, 8. And the theorem claims, in fact, the theorem claims that this is true for every graph, so in particular it's true for this graph, that I should be able to take the vertices and partition them into two sets so that the number of edges that cross those two sets, with one endpoint in one and one endpoint in the other, is at least M over 2. In this case, M equals 8. And so let's try and find such a partition. Well, let's put these two vertices in A. The remaining vertices go into B. And where are the edges that cross? Well, here's an edge that has one endpoint in A and one in B. Here's an edge that has one in A, one in B. Here's another one, and here's a fourth one. So that's a partition of the vertices into two sets, so that there are 4 edges that cross between these two sets. In this case, 4 is half of 8, so the theorem is true for this graph. And the claim is that this is true for every graph. And if you think about this for a while, you'll realize, well, that's a kind of a bold statement, right? I mean, if I give you a graph, it's not even obvious how you would do this partition. Graphs are big, complicated things. They can have, there's lots and lots of them. So how would you even get such a partition? And you might think about coming up with some kind of greedy thing where you put a vertex in A and then you put all its neighbors in B, so at least all the edges on that vertex cross this thing. And then the neighbors of those guys, you might put those back in A, except that some of them might already be in B. So it's really not obvious how you would do this. Okay. So let's try and prove this some other way. And in particular, using the probabilistic method, and we're going to use this second version of it about expectation. Okay. So we're going to set up an experiment where we somehow randomly choose A and B. And in this experiment, the expected number of edges that cross from A to B will be m over 2. And so the conclusion then is, well, if over all the possible ways of partitioning from A to B, on average there's m over 2 edges crossing, then there's at least one way where there's at least m over 2 edges crossing. Okay. So let's do it. Toss a coin for a fair coin for each vertex in G to determine whether it goes in A or B. B. It's a really easy experiment. All right. So that's how we define our set A and B. And let X be the number of edges, and I'll just keep using this term, cross, meaning that the edge has one endpoint in A and one endpoint in B. So we want to prove that the expected value of X is equal to m over 2. So we'd like to figure out how to write this, how to compute the expected value of this thing. So any suggestions on how we do that? So when we want to compute the expected value of a random variable, and the definition of that random variable begins with the number of something, what do we usually try? You guys know this. We've done it a million times. Indicator variables. Right? So I'm trying to count the number of edges that cross AB. So let's just define an indicator variable for every edge in the graph that tells me whether or not it crosses AB. So let's say for each edge E of G, define XE to be 1 or 0. It's 1 if E crosses AB, meaning it has one endpoint in A and one endpoint in B, and it's 0 otherwise. And then, of course, if I want to know how many edges cross from A to B, well, I just add up for each edge the value of this indicator variable. Only the ones that cross will contribute something, and they'll contribute exactly 1. So this is just E for every edge E in the edges of G, XE. What do we always do next? So we have the expected value of a sum. It's, especially when we've been using indicator variables like this, you always then take the sum of the expected values, especially when they're indicator random variables, because then they're really easy to compute. So we sum over all the edges again of the expected value of that random variable that tells us whether or not that edge crosses. Okay, this random variable xe. So I've got this edge E. It maybe has endpoints U and V. And I would like to know what's the probability that U is over here in A and V is over here in B. Well, what determines where these things go? Well, I tossed a coin for U. If it came up heads, then U goes in A, otherwise it goes in B. And I tossed a coin for V. If it came up heads, V would be in A, otherwise it goes in B. So in particular, if U's coin comes up heads and V's coin comes up tails, then that edge is going to cross, right? U is going to go in one of the sets, V is going to go in the other. Also, if U's coin comes up tails and the other one comes up heads, then that edge is going to cross. So as long as the two coin tosses are different, I get different outcomes for these two coin tosses, then that edge is going to cross. So if I toss a coin twice, what's the probability that the same thing happens both times? Or that something different happens the second time? Yeah, it's a half. If you like, it's 2 out of 4 because I just said it's heads, tails, or tails, heads of the 4 possible outcomes, or it's the second one has to be different than the first one, and the second one is equally likely to be heads or tails, so it only has probability of half of being the same as the first one. So that means that the probability that this indicator random variable is equal to 1, that probability is equal to a half. That means the expected value of this indicator random variable is equal to a half, which means that the sum we're looking at here is the sum over all edges of 1/2. How many terms are there in this sum? Well, the theorem tells us G is a graph with m edges. So this is m divided by 2. Okay. So then we finish up with for the random partition that we just defined, AB, the expected number of edges that cross AB is m over 2, right? That's this expected value of x that we just computed. And then we finish by using what's written over there. Therefore, there exists at least one partition such that the number of edges that cross AB is at least m over 2. if on average the number is m over 2, then it has to happen sometimes that I get something that's at least m over 2. So that's already remarkable. Because if I asked you to prove that by, giving an algorithm that takes any graph and finds this partition A, B, where half of the edges cross that partition, I think you'd have difficulty. I would have difficulty coming up with an algorithm proving that it works for every possible graph. Instead, all we had to do was define an experiment where, on average, what we want happens, which means that sometimes it must happen. So, on the one hand, this is very easy. There's nothing difficult to compute here. On the other hand, something really deep just happened. Yeah?
How do you know that those two vertices are connected?
So this is the sum over every edge of an indicator variable that tells us whether that edge crosses AB. So G is a graph. It has some edges. Some of the edges are there. In fact, it has exactly m edges. So for each of those edges, we just define this variable that tells us when we do the partition, does that edge cross the partition? So that it's given that E is an edge of the graph. Now the question is just what happened when we tossed the two coins for those two vertices? And that experiment puts them in different sets on different sides of the partition with probability a half. And that's true for every edge. So that means that the expected value of XE for every edge is exactly a half. So on the one side, this is all really trivial compared to the stuff that we've done so far. On the other side, there's something very deep happening here. There's a theorem here that says nothing about probability. It's a statement about every possible graph. It says doesn't matter what graph you give me, here's something that's true about that graph. And somehow we devised an experiment that proved that this is true for every possible graph. All right, and now even from this, maybe you can see how Erdős was able to do these things so quickly, just during the few minutes that are left in the talk, someone makes some bold conjecture here that says, oh, I think there are graphs that you can't partition the vertices into two sets where either of the number of edges that cross is not more than number of edges divided by 4. And 2 minutes later he says, no, you're wrong. It's actually, you can always get number of edges divided by 2. And you can check that that's actually the best you can do for some graphs. Okay. All right. So question about that before we move on? All right. Yep.
So in the two sets, do we always have to have more than one set, or?
Well, so this really talks about a partition into two sets, a left side and a right side, and you just count so partition means every vertex is in one of the two, is in exactly one of the two sets.
So can one of the sets have different one?
Sure, yeah. So it could be that the partition puts only one thing on one side. That's possible.
Okay, so we just look at the other.
Yeah, I mean, if that happens, so if you have a partition where this A is over here, B is over here, A contains only one vertex, then all the edges that cross are all the edges that happen to be incident to A. There's other edges that end up over here that don't cross. But if this is half of the edges, then that's the partition you're looking for. In fact, sometimes that's the best partition. If your whole graph is just a star like that, where A is adjacent to everybody and there's no other edges, then actually the partition that causes the most edges to cross is you put A over here by itself and then you put everything else on the other side. So that one gives you all of the edges crossing. So that's sort of an easy graph to do. Okay, so if you remember, like the first time we met, maybe, I showed you a couple of things, and one of them was this theorem about if you put 5 people together, and every pair of people is classified as they know each other, so you call that pair friends or acquaintances, or they don't know each other, in which case you call them strangers. Then in every group of 5 people, I can pick 3 of them who are either all friends, all 3 of them know each other, or they're all strangers. And that was a kind of cute application of the pigeonhole principle that starts by just taking any person and realizing that, well, that person either knows 3 people or doesn't know 3 people, and then working from there, you get it fairly quickly. But then the question is, well, what happens if I give you 100 people? Can I find a big group of them who either don't know each other, so they're all complete strangers, they never met each other, or they all know each other, they're a clique of friends who all know each other. So this actually is one of these questions that for a long time people believed that if you give me a group of n people, I should be able to find about square root n of them such that they all know each other or they all don't know each other. Square root n seems like a magic number somehow in these things. We saw, for instance, a theorem that said if you give me a sequence of numbers of length n, I can find about square root n of them that are either increasing or decreasing. So it has the same kind of flavor. So for a long time people believed this but couldn't prove it. And the reason that they couldn't prove it is that it turns out not to be true. And actually, you can get very large groups of people. So we'll switch from talking about people and friendship or strangers to graphs. You can get very large graphs that don't contain a large clique, so a large complete subgraph, and they also don't contain a large independent set, so a large set of vertices where nobody's adjacent to anyone else. So just so we get the idea, so the theorem that I just mentioned says, well, if you take a graph with 6 vertices, so here's, for example, a graph with 6 vertices, then I can either find 3 of them where every edge is in among that 3, or 3 of them where there's no edges in between them at all. So for example, in this graph, if I take this vertex and this vertex and this vertex, there's no edge between these 2, there's no edge between these 2, and there's no edge between these 2. So this is an independent set. In this case, of size 3. If I do just another quick example. So in this graph, if I take this one this one, and this one, then I see that between this pair there's an edge, between this pair there's an edge, and between this pair there's an edge. This is what's called a clique of size 3. So that theorem about groups of people really says that in any graph with 6 vertices, I can either find a clique of size 3 or I can find an independent set of size 3. And it seems reasonable that you should be able to find a big big clique or a big independent set, because on one side, if your graph has a lot of edges, you kind of expect that you'll find a big clique. And if your graph doesn't have very many edges, well, then you should be able to find a big independent set. At the extremes, your graph has every possible edge in it, in which case you find a clique that's the whole graph. At the other extreme, the graph has no edges in it, in which case you have an independent set that's the whole graph. And it seems kind of natural that maybe in between here, so you get n at one extreme, a clique of size n at one extreme, an independent set of size n at the other extreme, that maybe root n, you can always find one of these two of size at least root n. So that seemed like a plausible thing to believe, but actually not. So here's the theorem. For every integer, I think I have to say n bigger than or equal to 2, and every integer k bigger than or equal to 2 log n plus 1, there exists a graph with no clique of size k and no independent set of size k. So for example, just to give you some perspective, if I take n to be 1024, then the k that I'm looking at here is 21. So there are graphs with 1024 vertices where I can't find a clique or an independent set of size 21. Or another way to think of it, if you want to go back to groups of people, there exists groups of people of 1024 people where if I take any 21 of them, then inside that 21, there's going to be 2 people who know each other and 2 people who don't know each other. Because it's not a clique, so therefore there's 2 people who don't know each other, and it's not an independent set, therefore there's 2 people who don't know each other. The other way. It's not a clique, therefore there are 2 who don't know each other. It's not an independent set, therefore there are 2 who do know each other. All right. And the nice thing about this is even though this theorem is 60, 70 years old now, nobody knows how to build these graphs. So we know they exist. We don't know how to build them. And the reason we know they exist is because we're going to use the probabilistic method, the first part, where we're going to design an experiment that builds a random graph, and we'll look at the event that that graph contains a clique of size k or an independent set of size k. And we'll show that actually the probability that that happens is smaller than 1, which means the probability that it doesn't happen is bigger than 0. And if it doesn't happen, that's a graph with no clique and no independent set of size k. All right. So let's do that. Okay, so build a random n vertex graph by considering each of the and choose 2 pairs of vertices. Let's call those UV. And tossing a coin. To decide if the edge UV is in the graph. Okay. So I take the vertices of my graph, and let's call them 1, 2, 3, 4, 5. And I look at 1 and 2, this pair of vertices, and toss a coin. If the coin comes up heads, then I put this edge in my graph, and if it comes up tails, I don't. So maybe I consider 1 and 2, coin comes up heads, so I put this edge in. Now 1 and 3, I toss the coin, it comes up tails, so I don't put it in. 1 and 4, oh, it comes up heads, so I put it in. 1 and 5, maybe it comes up heads again, so I put it in. And now I have to consider 2 and 3, toss a coin, I don't know, heads, let's say. 2 and 4, let's say it's tails, so I don't put it in. 2 and 5, maybe it's heads, so I put it in. And I do this for every pair of vertices. Since there's n vertices, there's n choose 2 pairs that I decide whether there's an edge between that pair. So that's the graph. Okay. So now look at any subset of k vertices. So let's call those vertices V1, V2, up to Vk. So let's do some basic things. What's the probability that V1 to Vk form a clique? So I have a lot of vertices in my graph, n of them, but now I just look at k of them. Oh, I should check that. K of them, maybe k is 5, so I look at these 5 vertices, and I want to know what's the probability that they form a clique. That means that for every pair, there's an edge between that pair. Well, so that means when I consider this pair, I tossed a coin, and it came up heads. Probability of that happening is only 1/2. And then for this pair, I tossed a coin, and it came up heads. Probability of that happening is only 1/2. And for this pair, it also came up heads. That's only 1/2. And for this pair, that's only 1/2. And for this pair, and for this pair, and for this pair, and so on. So for each of the pairs, if this thing is a clique, that means that for each pair in here, when it was time to toss the coin to determine if that edge is in my graph, that coin came up heads. So how many pairs are there if there's k vertices here? K choose 2. And that means there's k choose 2 coins, all of them came up heads. What's the probability that that happens? So that is 1/2 to the, let's do it this way, k choose 2. Okay. And let's maybe examine this a little more closely. So 1/2, k choose 2 is k times k minus 1 divided by 2. Now I have some condition on k, so it's bigger than 2 log n plus 1. So that means this thing is less than 2 to the k. So k minus 1 is here, but k is bigger than 2 log n plus 1. So 2 log n plus 1 minus 1 is just 2 log n. And k is bigger than that, so if I put this in place of k, I'll get something which is, I'm dividing by something smaller, so getting something bigger. Let's not forget the divided by 2. So this is 1 over 2 to the k log n. So the probability that these things form a clique, it's exactly equal to this. It's exactly equal to this, but it is less. All right. What's the probability that V1 to Vk form a independent set? Well, what does that mean? That means I have these k vertices, and there's no edges at all in between them. So when I considered this pair of vertices to figure out, is there an edge here, I tossed a coin, and that coin came up tails. And the same thing happened when I did this pair and this pair. Every one of the k choose 2 pairs, the coin came up tails. So everything that I said about cliques, it's the same thing for independent sets, except that instead of all the coins having to come up heads, now they all have to come up tails. But that happens with the same probability. So this is less than 1 over 2 to the k log n. Okay. All right. So now I could say, well, what about the probability that V1 to Vk form a clique or an independent set? Well, the probability that they form a clique is at most this. The probability that they form an independent set is at most this. So that the probability that they form one or the other is at most this plus this, which is 2 over 2 to the k log n. Okay. So far, so good? All right. Let me pause for 1 second. And do the following. Because I see a mistake coming up. Let me put a 2 there, and then everything that I said up to here is true, but here I get to put a here I should get an extra 1. Let me put a 3 there. 3, here I get an extra 2, and everything is true except there's a plus 1. Same thing here, there's a plus 1. There's a plus 1. And that is 1 over 2 to the k log n. And let me just write this a little bit more neatly. 2 to the log n is what? 2 to the log base 2 of n is n. So this is actually 1 over n to the k. So to make the calculations a little bit easier, we'll stick with we'll weaken it a little bit and just say k bigger than 2 log n plus 3. Then you get this thing. Everything simplifies down nicely. We get probability of this is strictly less than 1 over n to the k. All right? So, now I'm interested in the probability that this random graph G contains a clique of size k or an independent set of size k. Okay. So let's say let V1, V2, V3, all the way up to V n choose k be a list of the k element vertex sets. So for all the n vertices in my graph, let me write out the list of all the subsets of size k. It's a huge list, right? N choose k. So what have I figured out? Well, for each of these, this is a big V. It's a set consisting of k vertices. So for each of those, the probability that it forms a clique or an independent set is less than this. So, so let's look at the probability that V1 is a clique or independent set, or V2 is a clique or independent set, or, and so on, or V n choose k is a clique or independent set. This looks complicated, and indeed it is. If we want to compute this exactly, we have a problem. And the problem is the probability of A or B or C or D and so on. If we want that exactly, in fact, even if we want just the probability of A or B exactly, there's a small trick, right? Probability of A or B is the probability of A plus the probability of B minus the probability of A and B. And when you have many of these things, it's a giant disaster. But one of the sort of first things that we learn is that this thing is less than or equal to, let's take the sum, I equals 1 to n choose k, of the probability that Vi is a clique or independent set. So there was this thing about bools, we called it Boole's inequality, that the probability of A1 or A2 or A3 or A whatever is less than or equal to the sum of the probabilities of the AIs. This was something we called either Boole's inequality or the union bound. And whenever we're faced with something like this, it's almost the only option we have, because principle of inclusion-exclusion just gets too complicated. But it's good enough for what we want. So Vi is a set of vertices of size k, and so we know now the probability that it forms a clique or independent set. So this is less than sum I equals 1 to n choose k of 1 over n to the k. So what's that equal to? Well, this is Nothing inside of here depends on I, so all we need to do is count the number of terms, and the number of terms is n choose k. Now n choose k, that is n times n minus 1 times n minus 2 up to n minus k plus 1 over k factorial. We've still got a 1 over n to the k. On top here, if I don't, if I replace all of these by n, I'll just get something bigger. So instead of putting n times n minus 1, n minus 2, if I just say n times n times n, I get something bigger. I'll get n to the k. On the bottom, if I don't even bother dividing by k factorial, then I will get something bigger. And so I get, in the end, so forget about this. Let these be big. I'll definitely only get something bigger here. And what am I left with? I'm left with 1. So, the probability that any of these things is a clique or an independent set is smaller than 1. So that means the probability that none of v1 through vn choose k is a clique or independent set. So let's think about this for a second. If none of these is a clique or an independent set, that means that none of these things happen, right? V1 was not a clique, V2 was not a clique, V3 was not a clique, and so on. So actually, that's the complementary event. These are complementary events. Either one of them, at least one of them is a clique or independent set, or none of them are. So that means that this thing is just 1 minus that probability. V1 is a clique or IS, all the way up to Vn choose k is a clique or IS. So 1 minus this number, but this number is less than 1. So 1 minus something smaller than 1 is definitely bigger than 0. So, what did we just do? We built a random graph, and we showed that in that random graph, the probability that there's no clique of size k, right? This is all the things that could possibly make a clique of size k. Probability that there is no clique of size k is bigger than 0. So that means of all the graphs we could have built, there's some of them, there has to be some of them that are have no clique or independent set of size k. Right? This probability of A is bigger than or equal to 0. Therefore, there exist graphs that have no clique or independent set of size k. How do you build one of these things explicitly? Nobody has any idea. Okay? So we can't even write an algorithm other than a randomized one to that just builds this random graph to say, okay, let's build this graph. Here's a large graph that has no large clique and no large independent set. We can build them explicitly so that they have no clique or independent set of size root n, but to make them this small, the only thing we know how to do is randomization. So I think that's an interesting and surprising result. It shows how much we know, at the same time how little we know about this kind of problem. And in fact, you'll learn later that finding the largest clique or independent set in a graph is an NP-hard problem. So even though this randomized thing seems to give you, there's no efficient way to check that the one I gave you actually doesn't have a large clique or independent set. There's a funny name for, or a funny phrase used to describe this probabilistic method, and it's useful for finding hay in haystacks. So normally you think of searching for a needle in a haystack. That's the hard thing to do because there's like a lot of hay in one needle and it kind of hides in there. This analysis here, you see that if I just put 5 or 6 or 7 here, then I can say not just smaller than 1, but smaller than a half or smaller than 1 over 16 or whatever, which actually means that almost all the time I'll get a graph that doesn't have a large clique or a large independent set. Okay. So that means almost all of the graphs there are don't have a large clique or a large independent set. They're the hay in the haystack. Almost every graph has this property, but as soon as you try and specify a particular graph, well, it might be one of those needles that has a large clique and a large independent set. Okay, so questions there? All right, and now the third application, which seems to fall, doesn't immediately fit into either of these categories, but is still amazing regardless, is the following. So let's start with a definition. For two finite sets x and y, the Jaccard distance is defined as follows. So the distance Jaccard between x and y is you take the intersection of x and y. So what do they have in common? Look at the size of that. Divided by the union, and you take 1 minus that. So let's look at two extreme examples of what can happen here. So, and this is a really common thing, is you have two sets of things and you want to know how similar those two sets are. And so that means you want some kind of distance between those two sets. And there's a few ways to do that. There's symmetric difference and things like that. But what you'd like is maybe something that just because the two sets are big doesn't mean they should be further apart than two small sets. So let's just look at an example here. So here's an example where x and y are completely disjoint. That means the intersection between x and y has size 0, right? That means then that the Jaccard distance between x and y is equal to 1 minus 0 over the union, so it's equal to 1. So in this case, the Jaccard distance between x and y is 1. And in fact, that's as big as it can be. On the other hand, if I have x and y, and they contain exactly the same elements, then the Jaccard distance is x intersect y over x, 1 minus that, x union y. Well, the intersection of x and y is this whole set, and the union of x and y is also the same set. So the second term is a 1 here. So this is 1 minus 1 is 0. And that's what we would like. I mean, if we're talking about what's the distance between these two sets, if they're exactly the same set, then the distance should be 0. In the same way that we think of distance, between points in space or in the plane, 2 points that are the same point, the distance between them is 0, but they, as they get further apart, the distance between them increases. So this looks like a reasonable way to measure distance between sets, and somehow it's always between 0 and 1, even if the sets are big or small, which maybe makes sense for a lot of applications. But one of the really important things about distances, at least the way we always think of distances, is what's called the triangle inequality. So the triangle inequality says that, well, the distance from x to z, so this is just the normal distance, so that's the length of this line segment if we're talking about Euclidean distance. Well, that's less than or equal to the distance from x to y plus the distance from y to z. Or if you like, it's always faster to go, or it's never slower to go directly from x to z than it is to go through some intermediate point y. So this is called the triangle inequality. So if you define some distance function on things, like for example this distance function over sets, if you want it to make any kind of sense, you need that this thing satisfies the triangle inequality. So the question is, does the Jaccard distance satisfy the triangle inequality? So the answer is yes. And the book includes 2 proofs. One of them I encourage you to look up, but I'll only mention very quickly how the proof proceeds. But in the end, it's the kind of thing that you can't really finish by hand. So the sort of brute force proof is to draw the Venn diagram. Call this x, call this z, call this y. And there's all of these possibilities for elements. They could be in all 3, they could be only in x and z, they could be only in z and y, or they could be only in x and so on. So you have some number of elements in here, some number of elements that are common to x and z but not in y. Right? And so give those things names, A, B, C, D, F, G. And so the triangle inequality says something like, well, the distance from x to z should be less than or equal to the distance from x to y plus the distance from y to z. And you can write down what that means. What's the distance from x to z? Well, that's something that has a denominator in it. So the union of x and z, that's a plus b plus c plus d plus e plus f. And remember, it's 1 minus whatever's in the intersection. So on top here you have b plus e. Or another way to instead of saying 1 minus this, is to say, well, that's exactly the same thing as if I take all of these things down here except B and E. So that's A plus C plus D plus F. And then you need to show that that is less than or equal to, and you write something like that, which captures X and Y. That gives you this big thing. You get another thing that captures Y and Z. And you rewrite that and say, well, that's the same thing as showing that if I take these two and subtract this one, that should be bigger than or equal to 0. And now it's no problem, right? You just find the common denominator and make sure that it's bigger than or equal to 0. In fact, I encourage you to look in the book because you get a numerator here which fills like 6 lines of text. There's squareds, there's d squareds, g squareds, all kinds of stuff. You get a big denominator as well. Well, the big denominator has all of these things in it. And somehow you argue that that thing is bigger than or equal to, whatever your answer is bigger than or equal to 0. It's horrible. There's no way you would do it correctly without the help of a computer math system. So let's think about another way of doing it. Okay. So here's the theorem. For any finite sets x, y, and z, the Jaccard distance from x to z is less than or equal to the distance from x to y plus the distance from y to z. And actually, the proof will be trivial if we remember actually some of the most easiest things that we've ever seen in this course, or things that are so easy we never even mentioned them. So here's one of them. Let's say let A and B be events. So in a probability space now. So events are sets. So if I tell you, but on the other hand, we also think of them as statements, like logical statements. So if I tell you A implies B, what does that mean in terms of sets? So A implies B means whenever an outcome in A happens, an outcome in B happens. But that must mean that every outcome in A is in B. So if I say A implies B, that's what the picture looks like. B contains A, because if there was one outcome in A that wasn't in B, then A wouldn't imply B, because if that thing happened, then B didn't happen. Okay? So that means that A is a subset of B. And that means that the probability of A is less than or equal to the probability of B. Because probability of A is the sum over all of these things, and probability of B is the sum over all of these things, but that include everything in A. That's a really easy thing. I don't know, numbers, they can actually be anything. So, if I is not equal to k, then I is not equal to j, or j is not equal to k. Let's think about that for a second. Why is that the case? Well, if I equals j and j equals k, then I equals k, right? So, so that's the not the converse, maybe the converse of that statement. So therefore, if I is not equal to k, then at least one of these two things have to be true, because otherwise I equals k. Okay? Nothing exciting there. But let's look at this. This is some event that we'll call A. I is not equal to k. And this is some event that we'll call B. So interpreting it in terms of events, and what we set up here, so this implies this. So the probability that I is not equal to k is less than or equal to the probability that I is not equal to j, or j is not equal to k. And this we already saw, well, we know a formula for this, but we'll be even lazier and just use the cheap version of that. Boole's inequality again, that's less than or equal to the probability that I is not equal to j, plus the probability that j is not equal to k. So nothing at all deep here going on. Really simple stuff. It will be easy in a few moments to get confused about why certain things are happening, but it's just because of this basic stuff. Okay. So here's what we're going to do. Let x1 to xn be a random permutation of x union y union z. So we have all the elements that we're talking about in this whole statement of this thing, is everything in x, y, and z. So let's randomly permute them. Okay. Let I equal to the, so all of the things in x, y, z, I listed them out in random order, so I'm sort of hopping all over all of this stuff in here. So let's take I to be go through this list, and I will look for the first one that shows up in x. Right? So I randomly permuted all the elements in x, y, and z, and maybe the first one in my list is here, and then the next one, the next one, the next one, and then eventually I hit one that's in x. So that's that index of that one, that's the value of I. Okay. Let j, so I do the same thing now for y. So again, I go through my list and I look until I see the first thing in my list that shows up in y. Guess what k is? K is the first thing in my list, It's the index of the first thing in my list that shows up in Z. All right. Here comes the punchline. Let's just look at probability that I equals J. So I go through this random list, and when does I equal J? Well, that happens when maybe x1 is in Z, x2 is in Z, x3 is in Z, and then x4 is here. I mean, it's in both x and y, right? Because in that case, the first thing that I see that's in x is x4, because everything else before that was in z. And the first thing that I see that's in y is x4, because everything else before that was in z. Okay? But wait a minute. What is this x4? How did I pick this thing? Well, I took things from my random permutation. I skipped over the ones that were in z until I found the first one that was in x or y. So that means it's just a random element in x or y. So maybe x4 could have been over here, or could have been over here. But I'm interested in the probability that it's actually here in both of them. But wait a second. That probability, look at how many of the choices are in x intersect y, and the set of options I had were everything in x union y. Okay, that's interesting. Now let's look at probability that I is not equal to j. Well, that's easy. These are complementary events. This is 1 minus x intersect y divided by x union y. Recognize this? Yeah. This is the Jaccard distance between x and y. Okay. There was nothing special about I and j here, right? I could have done this with I and k or j and k. So let's just see what we did. This statement that this thing satisfies the triangle inequality well, we just saw that this part that involves x and y, that's really just the probability that I is not equal to j. And if we do the same thing with y and z, we'll see that that's just the probability that j is not equal to k. And if we do the same thing with x and z, we'll see that that's just the probability that I is not equal to k. These are exactly the same statement. But this statement here, we saw already, it's a triviality. Right? It's there. It's true. So that's it. The Jaccard distance satisfies the triangle inequality, basically because of Boole's inequality. Almost magic. So I encourage you to go and look in the book. If I could log in here, I would show you the long proof of this. But literally, there's a half page of a formula that you get from that Venn diagram. And here, it really happened for free. I mean, almost for nothing. Okay, so that's a good place to leave it for today.